Okay, hello everyone. I'm Amin, and today we're going to talk about this paper called the Unpaired Image-to-Image Translation using Cycle-Consistent Adversarial Networks, or also we known it in the world of deep learning as the CycleGAN. So before any further ado, let's hop into it. So the first question is, what exactly is image-to-image translation? Image-to-image translation, what happens when we have domain X and we want to convert it to domain Y. Domains could be in different fields, such as images from the map, or ground images and the segmentations, or also the field of horses and zebras. For example, we have here in our data set, and our overall goal is to somehow convert from one domain to another domain. So, what is exactly the problem here? Traditional methods that they use for image-to-image translation usually needed a lot of paired data. What exactly paired data is? For example, for every corresponding image from domain X, we also need an image in domain Y. And there are a limited amount of datasets that actually have these specific features. One of the examples is a cityscape dataset, which for every ground image, we have a segmentation image. However, not all the data sets are paired. For example, here you could see an image from a horse and an image from a zebra. As you can see, there's no way that we could somehow pair them together because the boundaries are completely different and it's completely not possible. So one of the big issues for this task is the lack of paired data. However, this paper introduced a method that actually did not need paired data. So let's go into the details. Now let's have a better view over the entire model. Assume that we have two domains, domain X and domain Y, and our objective is to have a network called network G. Well, also we can also call it as generator G, and our goal is to convert from the first domain to the second domain using that generator, which here we assume that domain X is a bunch of images and distribution from the zebras, and domain Y is the domain and distribution of the horse images. And the overall objective is to have a network to generate an image, a horse image from a zebra image. Also, the inverse of it should also be correct, which means that if we have another network called network F, which is also a generator, when it takes in an image from the distribution Y, or the horses in this case, we are supposed to generate a new image in the X domain or the zebra domains. So technically if we have a image distribution from Y after passing it through network Z, network F, we are supposed to have a new image in that field. Other than that, we have two discriminators called DX and DY, which DX detects if the generated image is real or fake from the X domain, which here you could see that it should guess if this image from the zebra is real or fake, which we know it's fake because it was just generated from the previous horse in domain Y. And there's also another discriminator over Y, which we call it DY, which checks if the image is real or fake. And as you could see over here, this image is real. And basically right now we have a generator and discriminator, and it's technically a structure of a GAN, and we already know how the GANs are trained and how the loss functions should work. And this game of GAN, generator and discriminator, how they train each other in order to improve their performance. Other than the GAN loss, there are other losses that they use in their model in order to improve its performance. One of them is a cycle consistency loss. What exactly this is? Assume that we have an image in domain X. We apply the generator G to the image in order to convert the domains from domain X to domain Y. After that, we apply the transformation or generator F to the outputted image. So we are assuming that we should eventually have another image in domain X. And as the output, we compare the result, which here we could see two images from the zebra domain, which one of them is real and one of them is generated. we calculate the difference between these two, and the difference is going to be an L1 norm, and this is going to be defined as the cycle consistency loss. And they do it in both ways. One of them is that assume that we have an image in domain X, convert it to Y, and again to X, and calculate the difference. And also in the reverse way, which they have an image in domain Y, convert it to domain X, and again to domain Y, and calculate the L1 distance, and that's another loss, and they sum it up all together. One other loss that they use in their model is the identity loss. What exactly this does is that assuming that we have an image from domain X, we apply generator F to it. The job of generator F was to convert from domain Y to domain X. So technically it shouldn't lead to any bad effects on it, and we should eventually get the same result, and we shouldn't have any change in the output domains. And this loss prevents from this phenomenon called mode collapse from happening. And this should happen in both ways, which we have an image in domain X and we apply network F to it, and we still should have an image in domain X, and also the reverse way, which we have an image in domain Y and we apply network G to it, and we should still have the same distribution Y in the very end. We use all of the things that we just mentioned for training our network. And in our case, we used the Cityscape dataset, which is quite different from the main paper. However, in one part of the paper, they mentioned that this application could be used on various datasets. One of them was this dataset that I found quite interesting because segmentation is one of the problems that in the field of deep learning has got a lot of attentions to it. And we use the hyperparameters exactly as mentioned in the paper, and we trained our model for 200 epochs. And in the first case, we didn't use the identity loss because in their model, they tried once with using the identity loss. In another case, they didn't use one. And I just wanted to reproduce their results, so I did the same thing. And this is the accuracy plot, and the results are the ways that you could see right now. The result for the ground image is not best, however, it's quite acceptable. But about the segmentation, it's not the thing that we could find really great. However, it's quite convincing that we could still see some patterns in their output. However, in this case, we didn't use the identity loss. In the next step, we actually did use the identity loss. However, we didn't restart our weights, and we fine-tuned our model with the new loss function, knowing that we have the identity loss. And we trained our model over another 50 epochs. One of the reasons that we chose 50 was because we already have expired 3 Google Colab accounts, and we didn't have any other Google accounts to try to train our model even more. However, the results were much better. As you could see, the results for the ground image is like not exactly as the one that it was in their paper. However, the details are quite good. However, the colors might be a bit different, and it makes completely sense because you're passing a segmentation image to a network in order to generate the results. And this image is quite good. However, the identity loss, however, it made a good impact on the ground image. The segmentation didn't have like much improvement over their output. Finally, we are going to compare our results with the one in the paper. As you could see, the image from here is from the original paper, and as you could see, when they only used the cycle consistency loss, their results were not that great. Both the ground image and the segmentation that they generated was a bit sketchy and didn't contain much details, and the quality was quite low. And this is quite similar to the thing that we had. Our results were not that great. However, you could see a little bit difference between our results and theirs. And but the point is, when they used other losses, for example, the identity loss and other things in this model, their results improved very much. However, our results did also improve, but the improvement was not as good as ours. Since their paper, I'm assuming that they trained it for a longer time. They had much more GPUs and a longer time to train their models. However, We had a limited usage for the Google Colab GPUs, and we trained it for about I think 16 hours, and depending on how much time we had access to our Google Colab servers, and we tried 3 different accounts in order to see which one performed better. And as you could see, I couldn't say that we completely reproduced the paper. However, the results is quite promising, and it's not like 100% acceptable, but it's not that bad. Since you could see the ground image kind of represents the output how it should like depending on what the input segmentation is, but the segmentation output is not that great. However, I believe that the ground image could be acceptable, but the segmentation maybe need a little bit more, and maybe the training, if I had more training time, maybe it will be possible to completely reproduce it. And another part that I wanted to produce was this table. However, I was not able to reproduce it, and the reason is that the output is supposed to be categorized, which means for each pixel in the image, there must be a specific label or a class. For example, you could see the purple represents the road, gray represents the buildings. However, my output was a continuous RGB value, which in the paper they didn't quite exactly mention how I was supposed to convert that image to a label itself. And since I didn't know those details, I was not able to reproduce this part of the paper. However, if I knew it, I might have been able to uh, maybe reproduce this table as well. But since there was no knowledge about how to convert those 3D RGB values into a specific label, this part was basically unproducible. And thank you very much for your time.